OK，
我去老师都就读啊，老师，
好，可以吗？一点麻烦。
可以啊。
好的 ，All right, great. Okay, so today I will start with chapter 2 about the axioms of probability. All right, so this chapter is to demonstrate how to establish a logical structure of probabilistic reasoning. Okay, so basically we would like to lay out the foundation or the framework in the theory of probability. Okay, so let me address this. So this chapter is to demonstrate. It's you. Okay, how to establish a logical structure of probabilistic reasoning. And probabilistic reasoning is quite different from deterministic reasoning. Okay, and probabilistic reasoning quite often occurs in everyday life. So, for example, we usually say that it's highly probable to reach to some goal or something like that. Okay, because it's many things we are actually uncertain about the occurrence of something. Okay, for example, if you have a job in the future and earn some money and you want to invest maybe some asset, okay, probably properties, or you may make investment in the stock market, and you don't know whether this is a good investment. Okay, so you have to estimate the probability to earn money. Okay, if the probability is low, for the sake of your knowledge up to date, okay, then you don't want to invest your money to that asset. Okay, so only in a high probability, as you estimated, then you will invest your money into that. Okay, so this is a kind of probabilistic reasoning. Okay, and we would like to establish a logic structures that tell you how to do such kinds of reasoning. Okay, all right, and so the probabilistic reasoning is for a random experiment. Okay. Okay, so let me say it in other words to establish. Okay, a so-called probability space. All right, including a sample space. And a sigma algebra of events and a probability measure on events. Okay, so we will explain concepts of sample spaces, events, a sigma algebra of events, and a probability measure of events. Okay, yes, please.
What is sigma algebra of events?
I'm sorry.
What is sigma algebra of events?
Oh, okay. So I will define that exactly later on.
I thought I was supposed to know that.
I'm sorry. Yep. So this is just a very brief introduction. So in this chapter, you should know, at the end of the chapter, you should know what is a sample space, what are events, and what is a sigma algebra of events, and then what is a probability measure of events. Okay, so that is the central concept you have to learn in this chapter. Okay. Yeah, so that's very good practice. If you have any questions, raise your hand immediately. Yeah, we are a small class here now, okay? So I hope to have an intense interaction in this classroom. Yes, please.
Is that related to random variable?
Yes, but random variable is a further concept. Yeah, I know you have learned some concept of probability in high school. That's also good, very good. Yeah, so so I would actually I will introduce. So probably I think in chapter 4 we will encounter random variables there. Yes. Okay, so next section is about sample space. And events. All right, so a physical random experiment we would like to investigate corresponds to a mathematical model. All right. Okay. So it's better to illustrate the main idea in terms of an example. So let me make an example here. Okay. there are quite a few examples in the textbook, so I recommend you to read it through it. In the classroom, I would like to raise two examples of different characteristics. The first one, okay, so let me address that. The physical random experiments here. Okay, it's about, I select one of the running experiments. Okay, so it's about flipping two coins. As we know, there are two faces in a coin, right? Up and down. Okay, in different country or in different value, the coin has different faces, but actually they have up face and down face, as you can see. Okay, so now this is the one experiment. Now the corresponding mathematical model we would like to establish. Okay, so the mathematical model. Okay, so we were concerned about first one about possible outcome. So if you do the one experiment, this one experiment is about flipping two coins. Okay, I have two coins. Okay, it's easy to have that. So okay, so this is the $10 coins in Taiwan, right? And you have two faces. Okay. All right. So you flip, you get outcomes, right? I suppose in general we say that a coin has two faces. One is called the head, the other is tail. Okay. So the possible outcomes. So we say possible outcomes. So let me address that. All right. So there are four ordered pair. Okay. Because we are concerned about mathematical modeling, so we would like to use mathematical symbol, right? We learned before to model the outcome. Okay. So there are four ordered pairs to represent possible outcomes. Okay, and in this way, we assume we are able to distinguish these two coins. Okay, because why? Because ordered pair, you have the first place and the second place, which corresponds to the first coin, the second coin. It's impossible, right? You can do that. For example, you can make some marks on the coins, right? So that you can do so. For example, you can label it, the first, the second coin, and you do the running flipping the two coins. So you know, for this outcome, you say the first coin shows up the head, and the second coin shows also a head too. Okay, and so they are four possible coins. Okay, so you should know that. Okay, now, and now, so what is a sample space? The sample space is the set of all possible outcomes in a random experiment. Okay, so that is the definition. So you collect all the possible outcomes together, all right, and you use X, big X, to denote the sample space, and as a set, so you just enumerate these four possible outcomes, all right, so that will be these four pairs. Okay, so now you establish the sample space of this running experiments. Now, so it's because this running space is very simple. So you can see the sample space is also a simple set. Now in many terms, we want to describe the outcome of a random experiment by verbal description. So for example, so we call events. Alright? Alright, so for example, the first event about one head and one tail appear. So we usually use a sentence to describe an event. Okay? So we say that one head and one tail appear in the outcome. Okay? So this is one possible event. Second thing is that there is at least one head. Alright? One head in the outcome. Yes, please.
Possible outcomes and possible events, they're the same thing?
Not the same thing. Okay, because we describe that say one head and one tail appear, which means that the possible outcome is either this ordered pair or this one. Right? It can be this or that one, right? So it includes two outcomes, two possible outcomes. Okay, and there is at least one head, which means that, well, either these outcomes occur, or this outcome, you get this outcome, or this one, but not this one, right? So 3 out of the 4 outcomes give you this event. Okay, good questions. The third one, the 2 flips, okay, have the same results. And of course, you get many verbal description about what happened after you do the running experiment. Whenever you do the running experiment, you get an outcome. Okay? And there are many ways to describe a property of the outcome. So usually, this is the verbal descriptions. Okay. Now, so this is the verbal expressions. All right? And because we want to establish a mathematical model so that, as you can see, each event can be represented by a subset of the sample space. Why? Because the sample space consists of all possible outcomes. Okay? So that the first event here, one head and one tail appear, right? So that the possible outcome would be these 2 ordered pair. Alright? So if an outcome is in this subset, we say that this event occurs. Okay. The second event here, there is at least one head. Okay, and so you get the subset. Okay, one. And about the third event, the 2 flips have the same result, so that you get head or tail. Okay. All right. Okay, so we say that so the outcome an event E is said to occur if and only if the outcome omega xe e. Okay. Okay. So all the verbal description can be described by mathematical language. Okay, because set fundamental concept, right, in mathematics, right, and so set, and in a set there are elements. Okay, so we will say omega is in, or sometimes we use this belongs to, right, the mathematical concept epsilon here. Right. Furthermore, events, right, connected, all right, or operated by logical operators, right? So there are three logical operators, simple logical, say and, or, and not. Okay, right? So if we have two or more events connected or operated by logical operators, then the result should be event 2. Okay. Right? So for example, the event that there is at least one head, or the two flips have the same results. Okay, the same results. Right? Is what? So this is E4. So E4 is that there is at least one head. So this is referred to event number 1. Okay, or two flips have the same result. Two flips have the same result corresponding to E3. Okay, and the or, okay, the logical or corresponding to the union in set theory. Okay, the and corresponding to the intersection. Okay, the intersection. Okay, so the union, so which means that we have so one at least one head, which is E2. I'm sorry. Okay, so that is H head and tail, tail and head, union head, tail and tail. Okay, this is the union, right? So or either the outcome is in E2. Okay, because if outcome is in E2, this which means that there is at least one head. Yes.
The statement 1 is the event E4.
E4 is this event. Yeah, we define this one. Okay, so we describe it. And if the outcome is in this state, which means that the two flips have the same result. And because we connect these two events together by OR, so which means that either the outcome is in E2 or the outcome is in E3. Okay, so OR corresponding to the union. Okay, and you can see so that it's so you take the union, you get and this happen to be the total event. Okay, so the X, the sum is called the total event. Okay, now any questions up to now? So now in this random experiments, the collection of all events of interest is what? So as you can see that because events can be represented by a subset of the sample space, and actually every subset of the sample space can be described as an event. Okay. So if we collect all events of interest, because the meaning of interest means that we like to study this kind of events. All right? And because this random experiment is very simple, okay? So so any subset, any event corresponding to a subset of the sample space would be an event of interest. So the collection would be the collection of all subsets of the sample space. And this is particularly is called the power set. Okay, and it's denoted by 2 to the S power. Okay. All right. So, and so in this case, including the empty set, all right, and the total event, the subset. So this event, which means that both flips gives you the head. Okay, so this one and this one. All right, so these 4 subsets corresponding subsets, all right, consistent of only one outcome. All right, and All right. Now we have 6 subsets consisting of 2 outcomes. All right, because 6 select 4 select 2 is 6. Right? Because I assume you have studied chapter 1, right, about combinatorics and permutations. Okay, and a subset consisting of 3 outcomes. All right. So we have okay. So that okay, so the size in this way, right? And it's that 4 body 6 0 plus select 1 plus select 2. Okay, so maybe I will list X here. Okay. All right, and this is sum is famous, right? So its value is 2 to the 4th power. Okay. Yes?
Is that symbol F?
Yes, F. F is the collection, because we want to collect all events of interest, right? What kind of event you are interested, you could put them together. And in this simple one example, you want to collect all possible events, right? And every event is corresponding a subset of the sample space. So that this collection F will be the collection of all subsets of X. And in set theory, the collection of all subsets of X is called the power set of X. And the notation is here, the power set. Okay, and I just write down, enumerate all possible subsets here. And you can see the size of this collection, right? If we see that, it's this serious sum, okay? This corresponding to the empty set, because you have 4 possible outcomes, you stack none of them, okay? So they are only these numbers, and you have 4 possible outcomes, right? And you want to form subset with only 1 element, so 4 stack 1, all right, here. And you want to find the number of subset with 2 elements, so you 4 stack 2 here. With 3 elements, you 4 stack 3. With all possible elements, which is total event X, so 4 stack 4, and this is equal to 2 to the 4th power. Okay, this is a famous identity you have that. Okay, so the exactness is equal to 2 here. Okay. Okay, so that means the 16, right? So in this simple running experiments, there are 16 possible events for you to study. So that is very simple. Okay, it's really very simple running experiments. Okay. So the complexity is low because only 16. But as you will see, if the running experience become to not very complex, just moderate complex, okay? For example, instead of flipping two coins, you throw two dice, and every die has 6 faces, right? And so if you throw 2 dice, possible outcome would be 6 times 6 is 36, right? You have 36 possible outcomes. And then the possible, so that in that case, oops, sorry, 36, right? So let me take, so if instead of, so if you throw 2 dice, okay, and so the size, so the possible outcomes would be okay, so the size is 36, and the power set okay, and 2 to the 36 power, so that would be, okay, it's about, because 2 to the 10 is about 1,000, right? About that. So this is becoming a very big number, right? So this is very big, 10 to the 10.8. It's just a large number. Okay, and so it's about several trillion events. Okay, so these events, each of them is an event of interest. Okay, so there are a lot of events for you to study. Okay, and this is just very simple one too, right? Only you throw 2 dice. And you consider the everyday life, okay, even though the summer space is still finite, but if the size of the summer space is 100, what happened? 2 to the 100. So what's that? It's 10 to the 30, right? So if you get, so if the size is 100, then it's about 10 to the 30. Okay, 10 to the 30 is really a huge number. Okay, really huge number there. Okay. So you need a mathematical structure. Okay, so if you do the exercise, all right, for example, the exercise I will assign for you in chapter 2, then you will see that the collection of all possible events or the power set of the sum space becomes a huge number. Okay, quite often. Okay. Okay. All right. So you know the reason why we need a logical structure or a reasoning framework is that we will be able to develop methodologies to deal with problem with huge complexity. Okay, and we still can achieve our goal to compute the probability of certain events about certain random experiments. Okay, any questions? So this example, flipping 2 coins, is quite a simple example. Okay, but it illustrates the essential idea we can have. Okay, so that This is just two extra examples. Another examples. Right. Okay. Now the next example I would like to take is about right, so the physical random experiments is to measuring the lifetime of a light bulb. Right, in working hours. Okay. So when you do the random experiments, actually, you pick up a light bulb from a factory, right? And then you put onto a circuit and turn the light bulb on. Okay, and you measure the lifetime, right? Okay, until the light bulb burnt out. Okay, so for this, so we like to. So what is the corresponding mathematical model? Right. First one, what are possible outcomes? Okay. Well, because we measure the lifetime. So the outcome is actually a numerical value, and this numerical value will be non-negative real numbers. Okay, you never have a negative number because lifetime always non-negative. Okay, so the sample space. Okay, actually is this infinite interval. Okay, because we know how to express the set of all possible non-negative real numbers, right? So this is called here. It can be represented by interval here. Okay, so the sample space is the set of all possible outcomes. Say, right? Because the possible outcomes are non-negative numbers. Now, possible events. Okay, so let's describe possible events. First one, the bulb, okay, is broken after 1,000 hours. Okay, so that if you do one experiments and the outcome, right, is that the bulb is broken after 100 hours, which means that up to 1,000 hours, the bulb is still alive. Okay, still alive. Second, we have to replace the bulb during the 500th hour, and the third event, the bulb is broken just moment of 600 hours and 30 minutes. Okay. By your precision, suppose the precision is at minutes. Okay, so you know that the bulb is broken just at this moment. And of course, you have many different verbal description about an event to occur, right? So that there are possible events you have. Right now, events as before can be represented by subsets of the sample space. Okay, right, so the first event in this example is that the outcome, omega is an outcome, and the outcome is greater than 1,000. Right? Because it say that after, right? Broken after 1,000. After. So it's greater than that. And this is actually the interval. This open interval, as we learned in calculus. Okay. The second event, okay, says that we have to replace the bulb during the 500th hour, so that during the 500th hour, which means that the left time is greater than 499. But less than or equal to 500. Okay, so in this time interval, okay, and so this event is represented by this half open, half closed interval. Okay.
Both are hours, 499 hour and 500.
Yeah, this is the moment. 499 hours at the moment. So because it is the 500th hour. Well, the first hour is from 0 to 1 hour, right? But when greater than 1 hour, there will be the second hour interval. Yes.
So any time in between.
Yeah, it is if you have the timeline here, okay, so this is 0, 1, 2, 499, 500, 1. So this is the first hour, right? The first hour, okay, first hour and second hour. And so here, this is the 500th hour here. Okay, so you have to know that. Okay, good question. And the third event, which says that the bulb is broken just at the moment of 600 hours and 30 minutes. So why is that? Okay, so that is exactly, this is so the unit is hour, so that is 600.5 hour. Okay, exactly, so that consists only one. And we can represent this by an interval, a curse interval here, right? So the left end and right end are the same. Okay, so corresponding to a point on the time axis. Okay, so this is 1 and force. Okay, so you can try your best. That you can see that I have a verbal description about the outcome of these running experiments, okay, which we call events. And every events can be represented by a subset of sample space. All right, and the same events, okay, connected or operated by logical operators such as AND or NOT are event 2. Okay, so we take one example. The event that the bulb is not broken after 1,000 hours is this event, the event 4, right? So we describe that. This is actually the complement of event 1. Not broken after, because event 1 is the light bulb is broken after 1,000 hours, and the not is the complement. Alright, and so that is the set of outcomes which is in between 0 and 1,000, including the 2 endpoints. So that would be 0 to 1,000. Okay, and so this is actually okay. So it's the sample space, but you delete in 1 because you say the complement. Okay, so that would be, so this is 1,000, and okay, so this is in 1, and the complement would be so this is E4, which is the complement of E1. Alright, so now in this example, the collection of all events of interest is, yes?
What is that symbol mean? The slash one?
The slash 1, the difference that it was, okay, good questions. All right. Suppose this is set A, this is set B. Okay, and the A minus B, so it's minus, say minus, is that omega in A
So by that logic, shouldn't that be 1,000?
Oh, yes, sorry. I'm so sorry. Okay, so, yep, such that omega is not in B. Okay, so that would be this one. So this would be A minus B, yes. Yeah, I'm sorry. Yep. Okay, so the collection of events of interests in this case is not the collection of all subsets of the S. Why? Well, because that this sample space is the size of the sample space we call uncountable, very huge. It is a huge subset in set theory, and so the collections of subsets of this kind of sample space is too huge to study. As you can see, even for finite case, you can see that even in finite case, if the sample space is size 100 only, then the power set of the sample space, if you like to collect all possible subsets of sample space as events of interest, then the size of this collection is already a huge number. Okay, even though this is still a finite number, but this is huge. Now, for sample space with a size which we call uncountable, which means that there are many points there. Okay, then we will face difficulties if we consider the collection of all subsets of this kind of sample as the collection of all possible events. Okay, so that for several, and it's actually technical reasons. Okay, and this technical reason is too involved, so which we will not address here. Okay, we will not address here. Okay, so however, so now we want to, now it's demanded that first of all intervals of the sample space, the sample is just like this infinite interval. So I have to say all subintervals must be in the collection F. Okay, I have to say F. Okay. So that we ask that every subintervals of this infinite interval must be in the collection of F. Okay. As we demonstrate that from the previous examples, you see, it's quite often to describe an event, and it happened that the mathematical representation of that event is an interval, okay? And actually a subinterval of the sample space, okay? So we ask that all subintervals should be in that. The second, for logical reason, if E is in the collection of event of interest, then we would like to do the logical operation not, so that the C complement, all right, which is minus E, is also in the collection of events of interest. Right? Because we usually want to do logical operations. And the third one, we want for countable unions or countable intersections of events in F must also be in F. Okay. Right? So this is reasonable, right? Because we want to connect events by logical operators and or and not. For not corresponding to the complement. For or corresponding to union. For and corresponding to intersections. Okay? And we are satisfied if we can do the countable intersections and countable unions. Okay? Because from the development of the theory of probability, we find countable logical operation will be enough for us to study the property of probability. Okay, so that we want, so whenever we want to establish F as the collection of events of interest, then this collection of interest F should, for this running experiments, should satisfy 1, 2, 3, these 3 points here. Okay, and these 3 points, we regard them to be very reasonable requirements. Okay, right? Because in our practice of probabilistic reasonings about running experiments, we like that these 3 requirements to be true. Okay? All right, and now, so the minimum collection of events of interest satisfying the above 3 requirements. Okay, this collection is called the set the Borel signal algebra of the sample space plus. Okay. Right. And denoted minus B. Okay. And I haven't defined sigma algebra yet, right? So, yeah, forgive me, but I will address that very quickly after a short break. Yes?
Is that Borel?
Sigma algebra. Borel, yes. B-O-R-E-L. Yeah, Borel. Sigma algebra. Borel is a great mathematician. He contributed a lot in the theory of probability. Okay. Okay. So that this sentence just say that yes, we have one, and the minimum one, satisfying these three requirements, because that would be enough, right? The minimum one, and the satisfying these three, okay? And this minimum collection of events of interest has a special name, okay? And it's called the Borel sigma algebra, okay? Of this special sample space. Okay. And then after a short break, I will define what is a sigma algebra. Okay, so this is a very special kind of sigma algebra. Okay, okay. So let's just, take a short break up to 2:40. Okay. Okay. Now we have considered two examples of different characteristics. You can see. So, so in a general random experiments, with a sample space, so for the sake of logical reasoning, the collection F of events of interest is required to satisfy three properties. First one is the sample space. X is an event in F. Right. And which is usually called the total event. Okay. So the total event is specific for the sample space. Second, if E is an event in F, then the complement of E, the definition is here, is X minus E. Okay? It's also an event in F. Third one, if in 1, E2, are events in F, so you can see you have a countable list of events. Then their unions is also an event in F. Okay. Now a collection F of subset of the sample space which satisfies the above three properties is called a sigma algebra, or sometimes people call sigma field. Okay, sigma, this Greek symbol, usually called countable. Okay, countable. Okay, so that you can see that we can do countable unions here. Okay. And you may be curious about why we did not describe the requirements of countable intersections, right? As required here, countable intersections. And you will see we will show a proposition that these three properties will imply countable intersections. Okay, later on. Okay. All right. So the three properties is the minimum requirements. Okay, it's just like a Euclidean geometry, right? When we learn Euclidean geometry in middle school, either junior or high school, that Euclid, this set of axioms, okay, and so all the theorems and properties can be deduced from that set of axioms. One salient example is that it says that through a point outside of a line, there is one and only one line parallel to the previous line. Okay, so that is an axiom which cannot be proved. All right, and so a lot of consequences of theorem can be deduced from this so-called parallel line axioms in Euclidean geometry. Okay, and so in our work, in many times we have to establish sigma algebra for our studies. Okay, and whenever you establish such a collection of events of interest that also called, you want to establish a sigma algebra, then how do you justify that this collection is indeed a sigma algebra? Well, you just check these three properties because this is the basic requirements. Okay, and so it gives you a very convenient tools for the justification. Okay, for example, maybe in a quiz problem or the midterm examination, I will ask you to prove or disprove a collection of events, whether it is a sigma algebra or not. Okay, so that's this, and with these three properties, then we can do logical reasonings without any difficulty. Okay, so now a remark is here because the empty set is the complement of the total event. Okay, we know total event is already in F, right? And the empty set is the complement. So by the second property, the empty set, right, is in F2. Okay? So it's called a null event. So the null events must be in any sigma algebra. Just like the total events as a requirement, the total must be in any sigma algebra. Okay? So by axioms 1 and 2. Okay, so this property, we know the normal event we call, let's say, called the null event. Okay, so it has, the empty set has a special name, null event, just like the sample space has a special name, the total event. Okay, yeah. Okay, so with these two axioms, we know the empty set or the null is an event in any sigma algebra. Okay, and a member of a sigma algebra of a sample space X is called an event or a measurable set. Okay. And the pair, sample space, sigma algebra. So now it's called a measurable space. Okay, so all these are names we have. Okay, and now I would like to write down a useful proposition for logical reasoning. It's called the De Morgan's law. Right, so let's write B a collections of subset of a set as where I is an index set. So the index I may be a finite set. For example, index is from 1, 2, 3, 4 up to n. Or the index set is an infinite set. Right? For example, the index set is the set of all natural numbers 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay? Or the index set may be uncountable set. Okay? So it can be arbitrary. Okay? So if we have a collection of subset of a set, then if we take the complement of the union of all EI. Okay? So this is the union. Then this is actually the intersection of the complement of EI for OI. Second, the complement of the intersection of all EI is equal to the union of all the complements of EI. Okay? So these two formulas, these two identities are called De Morgan's law. Okay? So let's see the proof here. The first one. Yes, please.
Can you briefly explain what those symbols mean? Maybe expanding on.
Oh, this is the union of all the isabai. The union together. Yeah, because for example, if the index says it's 1, 2, 3 up to n, okay, so the union is actually okay, if the index set is finite set, so the union of EI for all the I becomes to this. Okay. In the first case, second case, if I is equal to n, okay, if the index is this one, then I. Okay. and so this is E1, union E2, union into infinity. In general, if I is an arbitrary index set, then you have the same meaning. Just take the union of them. So you can see the proof. To prove that, so an element in the right? Suppose X is an element of this set, but it is in the complement, so which means that X is not in the union. An element is not in the union, which means that X is not in EI for all I in I. Okay? Because that if you see 3, E1, E2, E3, then X is not here, so that, which means that it's in there. So X is in here. Okay. Okay. So X is here, which means X cannot be in any of X not in E1, X is not in E2, X is not in E3. For every, for all, right?
It's difficult to imagine that just by looking at the equation, but when you look at the diagram, it gets very clear.
Yeah, I know. Because so this is a very special case. Yes. Yeah. Okay. So that's if this is not in. So X is in the complement of union. So this one. So this is actually the complement, right? The yellow part. Okay, and so you have this one for all. Okay, and so this is X is not in EI, means X is in the complement of EI, right? For all. And for all, so that means that X should be for all, so it's in the intersection.
The intersection of complement of EI denotes
the intersection. So you can see here, first of all, what is that? The complement of E1, right? The complement of E2 so this is the complement of E2. The complement of E3 so this is the complement of E3. And the yellow part will be the intersection of the three colors. Because the yellow part, yellow, where is yellow? This is yellow part. Okay, Okay, so you can see all parts will be the intersection of three colors: the red, the green, and the brick. Okay, the bricks. Okay, for example, in here, this part is the intersection of the brick and the green only, right? So it's not the intersection of the three. Okay, in here, this is the intersection of the red and the brick only. In here, this is the section of the green and the red. Okay.
So everything out of the circle is in the...
Yeah, it's in the yellow. Okay, so that X here, this is the yellow part.
So that's what I'm saying. So basically these two are the same thing.
Yeah, the same thing is if and only if only. So that's the identical set, right? So
I was confused because I thought these two are the same, right? Then that's what we are proving. So.
Okay. So that's why I have the two directions. Means if and only if means equivalent descriptions. Okay, so X is in there, if and only if. So I used equivalent descriptions, and one by one, and show that if an element in this set, then if and only if the element will be in the set. So that's two set will be the same. Okay. Similarly, okay, so X is in the complement of the intersection. Okay, because it is in the complement, so X is not in this intersection. Not, right? When X is not in the intersection, which means that X is not in EI for some I in the index set. For some I. Okay? So let me, okay. It's really said a little bit complicated. I used to move Venn diagram. Intersection. So the intersection and the complement. All right, so that will be so this is the why? Because here this is E1 intersect E2, right? In here. Okay. And X is not in the complement of the intersection. Okay? So X is not in the intersection. Okay. Right. And so X is in the yellow part. So S is either not in E2 or not in E1. Okay. So for some means that one, okay. Okay, and so this says that complement for some I in I. Okay, and for some corresponding to union. So X is in the union AI complement. Okay, so it's important here to understand that X is not in the intersection of EI, means that X is not EI for some I, means at least one I. Okay. Okay, and X is not in EI, means X is in the complement of EI. For some I, and for some I mixed union. Alright. Okay, so De Morgan's law actually is about logical reasoning, right? Because for all and for some. Okay, for all means intersection, for some means union. Okay. Okay, so this is De Morgan's law. We have proposition 2.2 point B. If E1, E2 are events in F in a sigma algebra, then their intersections, okay, is also in F. Okay. Proof. Right. By property 2, property 2, yeah. So if E is an event in F, then the complement of E is also in F. Now, because E1, E2 are events in F, so that means E1 complement, E2 complement, etc. are events in F. Okay, by property 2. Now, by property 3, their union, okay, so their union is also in F. Is that correct? Oh, sorry.
This proposition is the second statement.
Yeah, second statement. Yes. Because E1 is in F, so E complement, E1 complement is also in F, right?
Right.
Yeah. When E2 is in F, then the complement E2 is also in F.
Right.
By 2, second, yes. So by the second property, you know E1 complement, E2 complement, etc. They are all events in F. Now, this is a sequence of events in F. So their union, EI complement, we take the union, is also in F, right? By property 3. Right? Because these are events. Okay. Now again, by property 2, this union union, right? This in F. Yeah, the second property, okay. Now, by De Morgan's law, okay, we know by De Morgan's law, this law, okay, complement, this is become intersection, complement, right? Okay, because this is, think about this is event, say Fi, okay? So that the complement, and the complement of complement is itself, okay? Okay, is in F. Okay, because this one we know is in F, but this complement is actually the intersection of EI. Okay, and so we prove that we have. So originally, if E1, E2, they are events in this sigma algebra F, then their intersections is also in event F.
This preposition statement is the third statement here.
No, the proposition is not, because this is only we say about union only. And this is intersection. Okay. Okay. So we can deduce this the intersection, countable intersection properties.
That's why we did not add this, the fourth statement, because the third statement.
Yeah, yes, because I just list the minimum requirement. Yeah, because it is good for justification for sigma algebra. Okay. So this is the least thing you have to do. Okay. Once you check the three property has been satisfied, then this property must also satisfied. Okay. Alright. So it is just like when you learn the Euclidean geometry. Okay. That we have some simple axioms. And all the property will be deduced from that. Okay. Okay. So you can see that properties about events can be deduced from these three the fundamental properties we have about the sigma algebra. Okay. And the proposition to point B is just one illustration for you. Okay. All right. So I stop here. Okay. Any question before we leave the classroom? Yeah. Good. So I'll see you Thursday. So if you have any questions after the classroom, you can send an email to me or to our TA.